So, hello everyone, welcome to our first class or discussion session about coherence and quantum entanglement. So, myself Nilakshi Shanapati, your teaching assistant, I will assist you and to solve your problems, as well as we will discuss whatever part it is covered in the course, as well as whatever is not discussed, maybe need to discuss, and whatever will be helpful for your examination, as well as assignment, and to learn most importantly. So, before starting, I will, as this is the first class, so today I will introduce with the course, and we will have some initial chat between you and me, and then I will give some formal introduction of this course, and then we will solve. I will discuss few things which you require to solve the first two assignments. Then. I will move towards solution of two questions, like several parts of this question will be there, and then we will end up the session. So, and in between that, of course, as today is the first class, it will be a little bit informal. Maybe I will ask you guys what is your name and what do you do, and etc. We will have some chat, because our purpose is to learn, and this is a 12-week course of NPTEL. So we need to be like very serious for carrying over a 12-week course, because people get exhausted in between, but hopefully we'll be enthusiastic till the end of this course. And okay, so let's wait for a few minutes more. If some other people also join, then I'll start. Maybe 1 or 2 minutes. Let's wait for them. Okay, so let us start. Maybe whoever joins, let them join by the time we start our discussion today. So, mm, first, there are few important things which I will discuss, you need to know where we will get all these discussion session notes, as well as various other things I will share later on, which will help you to learn this course eventually. Also, these lectures will be uploaded in YouTube, so that link also I will provide you, and all the details you need to know first, because of course you guys will join this discussion session, but maybe somehow some person can miss some of one or two class, or maybe some part of the class. So then you can again and again revisit to the YouTube to watch the videos again, such that you can access it whenever you want to learn according to your preference. So okay, so so hello again, welcome formally to this course named as Coherence and Quantum Entanglement under NPTEL. So this course is taken by Professor Anand Kumar Jha from IIT Kanpur. He is the instructor, and he has extensively worked on and was working on in this area for several years. And I am your teaching assistant Nilakshi Shanapati from IIT Kanpur, and these are your discussion sessions and problem solving sessions, which is going to happen every Saturday 5 p.m. to 7 p.m. for the upcoming 12 weeks. So today is the 27th January of 2024, and week 1 we are going to take today, organize today. So before going to the discussion of regarding this course, I will want to tell you that there is one there will be one Google Drive folder where you will get each and every documents whichever I will share, I will upload, I will discuss here, as well as whatever you require, I will upload there, such that you can get all of the materials. And this is the Google Drive link. I can tell you that this Google Drive link and the YouTube videos will also. Okay, madam. Yes. Do you want anyone want to say anything? I will talk with you guys, but give me some time before I start. 1 minute, guys. I'm extremely sorry due to some glitch. Okay. 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 Wait a minute, guys. I will start sharing again. Wait a minute. Okay. So yeah, so as I was already discussing with you guys, meanwhile I lost somehow my connection, some glitch happened, and I am back, and sorry for the inconvenience. So in the meanwhile, I saw that many other people has also joined. So for them again, as this is the first class, so I will formally introduce today's class. Maybe most of the people have joined after 5 minutes, so let me introduce once again, and then I will, as I was telling and giving you some information, I will tell them again, and please note those things such that you can keep track of all of the documents and discussion sessions such to for your learning purpose. So yes, so this welcome to this Coherence and Quantum Entanglement course by NPTEL. This is a 12-week course which is starting today. This course is instructed by Professor Anand Kumar Jha from IIT Kanpur. He has spent all of his life in working in this direction, and myself your teaching assistant Nilakshi Chanapati from IIT Kanpur, and these are your problem solving and doubt clearing sessions, which is going to happen every Saturday on 5 p.m. at 5 p.m. to 7 p.m. So before starting with the course, as I was telling when I lost my connection, that there will be one drive folder link where you can find every discussion session notes, as well as many other things like I can give you some reference to study to learn this course more, learn this course. So those all of the things whichever I will upload, that there will be only one link, that is this drive folder link, which I have shared just now in the chat box. You guys can check in the chat box, and this Google Drive link, as well as this Google Drive link, as well as there will be some YouTube link where these discussion sessions will also be uploaded. Those things will be shared with your in your NPTEL portal via swam thing, whatever is there. But again and again, every day I will mention once that there are these things, such that you don't need to go and find where are those, although they will upload this thing. And there will be this YouTube channel link where you can find the uploaded videos. This is a YouTube link. So first one is a drive folder link for docs, and YouTube link for these discussion sessions. Okay. So as this is the first class, so I would like to talk with one by one with each of the participants, such that I may aware of the people whoever is attending, like what is your purpose to learn this course, and what in which standard or class or what you do, such that it will be easier for me to convey you in that manner. Well, although it does not affect anything, you can learn anytime, any place. So this is the in this course, first I will today discuss about I will give some formal discussion, like to motivate you for this course, and then we'll solve some problem which will help you to solve these two assignments which has already uploaded, assignment 1 and assignment 2. Although I will not directly solve all those things, because those are your quizzes or assignments with respect to which you will get the marks, and we'll decide that if you are going to get a grade and which grade you are going to get. So but this will be very similar to that. So the discussion sessions are much more important in terms of solving the problems along with the your original lectures. So for your one more thing, there is one thing which is called ask a question portal in the NPTEL, where you can go and anytime you can post your question. Some people has already started using that, but if you are not aware, then I would like to suggest that please do write your questions there, then we will be able to know what are your question and we will answer you. And if you want my mail ID also, I can share with you. Please do not use it for random in case of random things, but if you have any question, or if you want any guidance or discussion regarding this course, and if you want to learn more about this course and these things, quantum mechanics, quantum entanglement, coherence, then I am always welcoming to all of you people, such that we can discuss and you can learn more and more. So this is my mail ID. Also so there are the way to reach to us is this mail ID, and most importantly the ask a question portal in the swap portal of this course, where you will be in touch with us. So all right, and drive folder and YouTube link is already shared with you. Keep that in mind and keep track of the drive folder link. There I will upload many things. So I will get back to you soon to know that what maybe I can discuss now that like what is your background and what do you want from this course, and then I will like start discussing about this course. So first I can see Bharavi Snehal Khatri. Can you please unmute yourself?
Yes, ma'am.
Yes. So, Bharavi, in which class you are, or what do you do? Give a little introduction of you.
I'm in fourth sem MSc Physics, studying in Central University of Rajasthan.
Okay. All right. So, you want to continue your research in this direction?
Yes, ma'am.
Okay. So, next up is the Chandan Hegde. Can you please unmute yourself and give a little intro about you? That what do you do?
Hello, good afternoon, ma'am.
Yes. Good afternoon.
I am Chandan from Karnataka. I have completed my MSc from Karnataka University, Dharwad.
Okay.
And now I am preparing for national entrance exam test.
Okay. Okay. Great. So, you also want to continue in this direction?
Yes, yes.
Okay. Dhruv, can you please unmute yourself and give a short intro about you?
Yes, ma'am.
Yes.
Myself, Paldu Dhruv. I'm studying in BSc, second sem,
Okay.
mathematics major. I just wanted to learn about this
Great.
and see more that I can do.
And from which institute you are?
BKM University, Gujarat, and college is MD Science Portmandar.
Okay. Great. So, Mani Madhu, can you give a little intro about you?
Good evening, ma'am.
Yes.
I'm Manu, a lecturer in physics in a government polytechnic college, Dharmaburi, Tamil Nadu. I did my MSc in Madurai Kamaraj University and MPhil in St. Peter University, Chennai. I done my research in quantum entanglement at the MSc level. After that, at my MPhil, my research is quantum bipartite and tripartite coherent states.
Oh, then
So I
that
want
means
to-
you have background of this very well.
Yeah, ma'am. Yeah. So
Okay.
I want to continue this research. The forthcoming years, I want to join a PhD.
Okay.
So that's why I attend this course, ma'am.
Great. Very nice to meet with you.
I got a government job, so that's why. So next year only, I'm going to join.
Okay, that's great. That's great. Nice to hear from you. Then Naveen. Naveen, can you give a short intro about you?
Good afternoon, ma'am.
Good afternoon.
I'm Naveen Salokar from Dharwad, Karnataka.
Okay.
I just completed my MSc from Karnataka University, Dharwad, and presently I am studying for PhD entrance tests. I wanted to study this course, as I think quantum computing and this field will have a boom in the future, and I want to have a career in that field.
That's great. Okay. I hope you will fulfill your dream. Okay, next, Prashant Rathod.
Yeah, madam. Good afternoon.
Good
I
afternoon.
am Prashant Rathor, and I have done my BTech in Electronics and Telecommunication, and then I done MTech in Optoelectronics and Optical Communication in 2000.
Okay.
And present I am working in CROT, and already we have developed some product related to quantum communication in like discrete variable quantum communication. Like protocol, we made Coherent one-way and DPS protocol.
Okay.
And I want to do this course. Actually, I want to make some telecom system related to quantum teleportation and some protocol like measurement device QKD communication.
Okay. So
Thank you.
right now you are focusing on these things. Like right
Yeah,
now,
yeah,
what is your
yeah.
position? I did not get.
I am a group leader.
Okay.
So generally, CDOT is R&D center.
Okay.
It's comes Ministry of Telecommunication. So generally my background is optical communication field.
Okay. Okay. That's very nice. Very nice. I think you have written something in the Ask a Question portal also, right? You are that person. I thought.
No, just I have replied.
Yes.
Somebody
Yes.
asked
Yes.
us. Yes, yes.
Yeah, okay. Oh, nice
So
to
just
meet you.
I have little background in some
Yes.
computer mechanics. So just I want to learn.
Yes. Sure.
Thank you.
Very nice. Very nice to meet you. And Shubhajit. Shubhajit, can you please
Yeah, good
unmute
afternoon.
and tell? Yes.
Yeah, ma'am. Good afternoon, ma'am.
Good afternoon.
Ma'am, I am from BSMS student, third year physics major from either Trivandrum.
Okay.
So I have already done my this quantum mechanics. First, there's like two parts: quantum mechanics 1 and quantum mechanics 2. So I have already done quantum mechanics 1, and that's I just want to extend my knowledge. That's why I'm just
Okay. So
join this course.
in which semester you are?
Ma'am, I am in the 6th semester.
Okay. Okay, that's great. Okay, so I think these are the people who have joined today's class. Okay, I hope that every one of you already have like a pretty good amount of knowledge in quantum mechanics, and all of you want to build a career in this direction. So all of you will continue this course up until 12 weeks, hopefully, and we'll have a very nice journey. And at the end of this, I hope that everything, whatever we want to convey, I think you guys already have gone through the syllabus of this course. If you don't, then you can check this drive folder link which I have already shared with you. There the syllabus is given, that whatever it will cover up in this course. So of course, at the end of the course, we will learn about coherence and quantum entanglement, both the theoretical and experimental perspective as well. Because I think that doing theory and doing practically in like with the experiments, there are some difference also, because you will learn a lot when you will see it and do it by your own hand, of course. So but for that we need a lot of background to build up that position. So let us start today. So the thing is that classical mechanics is overall a very successful way of describing physical phenomena already, in the sense that majority of modern engineering problems and situations, they do not require the quantum mechanics. But the beginning of this last century is already started becoming clear that actual physical reality goes beyond the classical description, and it requires a new way for its description. This way of describing physical phenomena is now what we know as quantum mechanics. Although, for most of the part, it seems quantum mechanics is required to describe physical phenomena in the microscopic world, while classical mechanics is sufficient for the macroscopic phenomena, modern experimental advances have now established that there is actually no differentiation on the length scale. This is not the correct approach that we generally take in our BSc MSc days. What mistake I did in my BSc MSc days, not mistake, but most of the students do that we thought if it is visible length, or we can consider it as 1 meter, 2 meter, or some millimeter even, whatever we can measure with our eye and with some measurable thing like screw gauge or anything, whatever if you can measure it, then we say that it is macroscopic world, and quantum mechanics does not fall into this world. And whenever we go to the microscopic world, maybe it's photon, maybe it's atom, whatever, then we say that it is classical mechanics. But this is not exactly true. The truth is that whether it is macroscopic, whether it is microscopic, quantum mechanics is the ultimate truth. But we, in this macroscopic world, we get such kind of boundary, such kind of condition, which as a whole can give us a classical perspective. That means classical mechanics is a special case of quantum mechanics. Okay, so in fact, like, it is now understood that the quantum description is only the correct description, even whether it is physical system in the macroscopic or microscopic, that does not matter, in even with the study of the experiments, not only theoretical. If we just consider like a light beam is coming, and light beam, we consider it as E0 cos omega t minus kx. Every one of you know that, as every one of you have physics and mathematics background. So we consider it as an electromagnetic wave, and when it is true as a wave, then we call it as a classical description kind of thing, or the simply the electrodynamics, which can give us all the information. Now the question is that in the electrodynamics, in this domain, should we say that it is not quantum mechanics is not true there? No, because suppose the light beam is coming, it consists of several millions of photons, and now I am cutting down the beam and getting a smaller and smaller and smaller version of the beam. Now if I have a very small beam which is a length of some millimeter, then also it consists of some photon. If it is 1 meter, then also it consists of some photon. But then we can go to the wave description of it. But photon nature is always true. So neither the fact what it becomes ultimately is that it is neither wave, neither particle. It is a wave particle duality, which is the ultimate truth. So macroscopic and microscopic world cannot differentiate between classical mechanics and quantum mechanics. This is the first myth we had, and we need to drop now. Okay, so now next thing is that, then what are the main differences between classical and quantum mechanics? Classical mechanics is a deterministic thing. Like, classical mechanics is in principle deterministic, whereas quantum mechanics in principle is indeterministic. If the complete information about the initial condition of a classical system is known, it is in principle possible to precisely predict its future evolution. At T1 you can know at Tn. But this is not true for quantum systems. A quantum system remains indeterministic in general, and its future evolution cannot be exactly predicted. In fact, this true indeterministic nature of the quantum mechanics is now used to create true random number generators. In classical approach, whether you are applying whichever algorithm, Monte Carlo, whatever, then nothing can actually generate the random number. Whenever you are going, when you can go to the 1 minute, somebody wants to join. Okay, so whenever you go to the go to the quantum level, like superposition state is also come to the play, then only you can use the true, then only you can make a true random number generator according to your application. So this was the first thing, the determinism, which can differentiate between a classical mechanics, quantum mechanics. Then the effect of measurement. Like in case of classical description, an act of measurement does not affect the system. In case of quantum description, one cannot make any measurement on the system without interacting with it. So let me write first the things, what are the differences between I hope you can see my iPad there. So the main differences of classical and quantum. So today is the first class, so that's why I am motivating and giving some in general discussion in the first half of an hour. Then we'll go to the main course and mathematics, and also we'll solve problem. Okay, so you need to learn in that approach that in the first few weeks the course will go in very slow manner. Okay, like if you whatever you are doing, you try to learn that very in-depth manner, such that when we'll run the course after 1 month, then it will be very fast. So you need to catch them up, and if you start negotiating all these things from the beginning, then it will be difficult. I know that everybody of you are very well aware about this field, and what I get to know just right now, and you all guys are very serious about it, so this is not going to happen for you. But I am just telling that first few weeks it will be very slow, and then the fast thing will come. And at the in the beginning we are discussing about the quantum and classical and all those things. Somewhere it will help you, because I can assure you that even the current scenario in this field is that there is no such very good boundary between coherence and entanglement, and this is a very open kind of problem. So to understand and feel the classical mechanics and quantum mechanics, where the transition and where we can consider what, and how the quantum mechanics is playing the role, and how we are doing the experiments by saying it as a quantum experiments, those if you want to understand all those things, if you want to feel that thing, then first you need to start with the very basic, that is the main differences of the classical and quantum mechanics. This is very important. So first thing is that determinism. So as I have already told, classical mechanics is in principle deterministic, and quantum mechanics even in principle is indeterministic. Okay, I am writing just the headings, not the total thing. Then the effect of measurement. So effect of measurement, as I have already told, that if you know the like if you know that at the t1 time this is the condition and the classical body is there, then in classical description it can you can sorry, in case of effect of measurement, if you measure the body at t1 time, then it will not affect it is not going to affect the t2 time thing. But in case of quantum description, one cannot make any measurement on the system without interacting with it, and that is the main disadvantage, as well as this is the weirdness of the quantum mechanics. We cannot say it as disadvantage also, because these thing happens. That's why the QKD or quantum key distribution or quantum secure communication protocol can be developed. Okay, so second thing is effect of measurement. Now in case of this, if you if the act of measurement changes the system in general, then the only exception in when the system is one of the I mean there can also be some exception if the system is one of the eigenstates of the measurement operator corresponding to some physical observable, then you can find that even after measurement also the state is same like previous, not changed. So those kind of technical details we will revisit again and again, but I mentioned this thing just to know, make you aware about that nothing is eternal truth here. Everything will change from system to system, condition to condition, situation to situation, and so on. Okay, so now next thing is that equation of motion. So in classical mechanics, the equation of motions are in terms of real variables like position, momentum, etc. When sometimes sometimes we write the equation of motion in terms of complex variable, it is only for the sake of mathematical convenience in case of classical description. On the other hand, if you consider quantum mechanics, the equation of motion in equation of motion in quantum mechanics is written in terms of wave function, which intrinsically an abstract object. How will you tell what is a wave function? If somebody asks me what is the definition of wave function, if I was a BSc student, I would have told this or that. Even if I was a MSc first semester student, I would have told this or that. But at this moment, if somebody asks me what is a wave function, what is the definition of wave function, I will say literally I don't know like how to define it. Okay. So so there comes the main thing that we in generally write the equation of motion in quantum mechanics in terms of complex notation. Okay, so and one interesting thing is that if as this is there is some complex counterpart of this kind of wave function, that is what makes it actually mathematically easier, although it was not supposed to happen, but somehow it happened. Okay, so now next point is duality. The first thing is that this is a very important thing, is the classical description is free from duality. There is no concept of duality in classical mechanics. A system which is described by Newton's equation or wave equation, these are the two main things that happen in the classical description, then whatever the condition you will give, you will get a solution according to that. There is no duality in classical description. But duality is the most essential feature in quantum system. As I have already mentioned, it is neither wave, neither particle. This is wave-particle duality. So, simultaneous presence of particle and wave is what actually making it a weird thing. So, this is one of the most important thing is duality. Now, fifth is that superposition. Wave mechanics studies the dynamics of waves. The equation that describes the dynamics that we call as wave equation. And we all are aware about Maxwell equation. There are E, B, electric field, magnetic field. There is time evolution of the electric field, magnetic field, etc. Now, one most important phenomena we can see in this wave scenario is interference. Believe me or not, maybe now you will not believe me, but at the end of the course you will believe me that this is the most important phenomena, whether it is classical or quantum. Wait a minute, somebody wants to join. Okay, so interference, I have highlighted it so much because this is the most important phenomena, whether it is classical or quantum. Although this is what we understand up until BSc or MSc, that interference we have learned during our wave mechanics course or wave optics course. But you will learn today that it is not about wave concept. Even if we consider photon concept, like photon are coming through double slit experiment, then also what we observe is interference, and that is what it makes it most beautiful phenomena in this one of the most beautiful phenomena that occurs in nature. So classical mechanics description of interference is absolutely based on the division of amplitude. Let me change my slide. Okay, so classical mechanics description is based on the division of amplitude, which necessarily implies the division of energy. On the other hand, the quantum mechanical description of interference is based on the division of wave function. Now, how will you describe it? It does not imply division of energy, since a photon cannot be divided. We know if it is one photon or two photon, then it is one or two photon. We cannot divide it in a 1.5, 1.25, 2.25, nothing like that is possible. So, although it is very difficult to imagine or believe that how is it even possible that if a wave is coming in the classical nature, what we observe through the double slit, the two slits, then what we observe is this kind of pattern which we call the interference pattern. Now, can you believe that if photon by photon are coming and falling and we are gathering it over the time, like t1 time, there are this is t1 is lesser than t2, of course, and in that time we cannot understand that if it is an interference pattern or not. At t2 we are little bit kind of understand that it is a interference pattern. In t3, at t3 we can see that this is a interference pattern. So whether it is coming a classical light, like nothing can be classical light, like whether it is coming light as a whole, like a torch light kind of thing, or whether it is coming a one by one photon, both of the thing provide us with a beautiful interference pattern. One case, classical interference, it shows division of amplitude, which is the division of energy. Quantum interference, it tells about division of wave function, which is not equal to division of energy. And now the what starts between a classical and quantum phenomena, which one is truth? Now experiment comes into the role, come into its play, that what if we can check these two scenario, then what we actually observe and which is the ultimate truth. So by that you can demonstrate this kind of experiments in your lab. We have already, of course we have done this kind of experiments, so you can obviously get the interference pattern. And many people who sometimes disagree and ask many weird question. You can also ask any question that if you have, that how is it possible, and if it is really even possible or not, then if you believe me, all these things are really possible, and this proves that quantum mechanics is the ultimate truth of this nature. So classical mechanics is just a special condition of this quantum mechanics. Okay, so now if the field is deterministic, like whatever I am telling as a whatever I am telling as a classical field or a torchlight, then interference is perfect. Okay, now but however, if the field produced by real sources are more or less random, then also we see that interference pattern only, but we need to acquire some more photons and we need to wait to observe the interference pattern. Okay, so somebody has asked in the ask a question portal also that how is it possible, or how single photon level we achieve and all those things. So for that there are technical things, and of course if I am saying single photon, that does not mean a single photon here does not mean a one photon Fock state. Here it is not true. Okay, here single photon, if I am talking about, then this single photon means like we have set up some threshold, we have some energy and we know what can be the photon, a single photon value, energy value at a particular omega, then according to our threshold, attenuation of the light and detector gain, we can set up a particular threshold corresponding to a single photon detection, which we are calling as a single photon here. So I have answered the question in the portal, ask a question portal. You guys can see that what was the question and what was the answer. So I want to just to clarify you, one minute. I think again the thing has gone. 1 minute, let me. I am extremely sorry. I don't know how the internet is so unstable today, even at here. But sorry again. All right. Let me share my screen of my writing screen also. There also it is not connecting. Okay, maybe. Okay, now it's fine. Okay, can you see it? Yeah, fine. All right. Okay, so if the field is deterministic, interference is perfect. However, the fields produced by real sources are more or less random. The reason for this is that a real physical source consists of infinitely many emitters, like a beam of light is consisting of many photons, all of which emit in a statistically independent manner. As a result of the total emitted by the source becomes random. In the case of random fields, interference occurs to the extent that the fields at two different space-time points are how they are correlated. That's where the coherence comes into the play. Now, the nature and the degree of this correlation is described through a function which is called coherence function. And the equation that dictates the dynamics of coherence function is known as Wolff equation. Till now, you are aware about wave equation. Now, whenever you are talking about dynamics of coherence function, then you will talk about the similar kind of equation which we call Wolff equation. I am right now telling about a overview of today's discussion, what we are going to learn in this week and next week, and the problems we are going to solve. This equation will come. That's why I am mentioning this, and I will of course write this also. Give me some time as I am giving an overview of this course at this moment. So coherence as a requirement for interference remains the same both in classical and quantum description. So this again, let me write it in a highlight manner, that coherence as a requirement for interference remains there, whether it is remains like for interference remains whether it is classical or quantum. Can you guys read my handwriting? Otherwise I need to write it in more perfect manner. I'm writing very hand waving manner at this moment. If you feel any discomfort with my handwriting or anything, my voice, my video, then you can raise your hand or write into the chat box or directly unmute and tell me. I'll be cautious about that. Okay.
Nikarshi, this is readable, no problem.
Okay, thank you. So coherence as a coherence as a requirement for interference remains the same both in classical and quantum description. This means that the two interfering field amplitudes in the classical theory and the two interfering wave functions in the quantum theory need to be mutually coherent for the interference to take place, whether it is classical, whether it is quantum. Within quantum theory, the concept of coherence can also be cast in terms of indistinguishability arguments, which say that if a photon in two separate alternatives remains indistinguishable, that is, if there is no way of figuring out which particular interfering alternative a photon is taking place, then the two alternatives are mutually coherent or therefore interference will take place. So indistinguishability, this is also a very debatable comment, like indistinguishability, these kind of features, but that is one another approach to look at the interference. But let's not go into the debate. This is very clear that whether coherence is a requirement, whether it is for the interference, whether it is classical or quantum. Now, what does coherence means? Another important thing. Coherence. So coherence is the degree of the orderness in a random field. Okay, so within classical description, randomness is in principle removable if complete information about the systems becomes available. But it is not always possible to obtain the complete information about a system, and this is why one studies random fields through correlation function. Maybe right now, as we are talking about second order, very intensity, we naturally talk about intensity and interference, but you will realize when I'll solve, and maybe you have already seen the lectures, that when you work with the interference, then actually the information lies into the cross correlation function, which talks about the coherence function. And if you correlate between the classical description of with the wave, like just a wave behavior of wave equation kind of things, and simultaneously write the quantum equations, quantum equation by the bracket notation, then simultaneously you can observe that that coherence function, whatever we are talking about, that's what actually represent the density matrix also. We'll obviously learn that in this course, that how to calculate, because if you want to generalize something, then you cannot do that by classical mechanics. Like you have information of intensity pattern in the interference, but you don't have the phase information. You can retrieve that somewhat in terms of the coherence function, which is a cross correlation function. You have already gone through the lectures, I hope. And when we will go to the quantum description, you will see there is nothing like for a pure state we can write that in terms of wave function, but even if it is an event general state like a mixed state, then even we cannot write that in terms of wave function. We need to only write the density matrix, and then we'll go to the 4 vector form of 4 cross 4 matrix or 2 cross 2 matrix, depends upon the dimension of the basis. So all those things will come after a while. Okay, so for some classic now let's come to this concrete word, that coherence is the degree of orderness in the random field, and within the classical description randomness is in principle removable if complete information about the system becomes available, but it is not possible to obtain the complete information about a system, and for that we need correlation function for sure. Eventually you will understand the importance of coherence function over the time. In quantum description, the randomness is not removable even in principle. Okay, as it is not, so the importance of coherence function becomes more. How? That you will again get to know, and when you will come to know about the entanglement, then you will see the weirdness in terms of again coherence function. So this is very important. So the only concrete quantity that can be studied within quantum theory is anyway correlation function. For some classical for some class of fields, suppose classical and quantum description of coherence have same average result, at least in the highlight level. Whenever I am calling highlight level, that means lots of photons are there, and we can consider it as a E0 cos omega t minus kx, thus the electrodynamics, thus the highlight level, and thus it automatically become wave mechanics and classical description is happening. But if we go to the single photon level, 1 photon, 2 photon, 3 photon level, then again we need to follow the quantum description, and then Wolf equation becomes much more important than the wave equation. Okay, so I think I have motivated you enough with the differences between the classical and quantum mechanics, as well as what we want to do, where the coherence come into the place, and when we'll get to know about the density matrix and the quantum description of it, and why we are talking about coherence. Those those people who have already a background of coherence, maybe they already know about the coherence, but to know quantum entanglement, it is very important to know coherence. And those who does not know, then I think this will be a good motivation for you to first learn coherence and then eventually move toward the entanglement. Now basics of the probability theory is very required here in this course, because whatever you are going to describe in terms of coherence function, all those are nothing for a stochastic field with 2-point correlation and the probability distribution of those events. And you know very well that in the quantum description, the statistics is very important, because nothing is truly known, rather we know the weightage of a certain event or certain state, for whatever you say. So just to revisit it, that if you toss a coin, or if you drop a ball inside a box, then you can get that first time it will drop at this one position, second time is this x2 position, and eventually each and every time it will go to some other point, but some again and if you plot a distribution of that, like x versus px probability, that how many times it has fallen into the 1, how many times in 2 and 3 between a and b, then you will get a probability distribution, and you will see that which has what kind of weightage, and this is some sort of biased in which position. Okay, so that is the basic that is the basic of probability theory. And you know that completeness theorem, orthogonality theorem, all those things are there in the quantum mechanics 1 itself. I hope this is the this was the prerequisite for this course, that a basic quantum mechanics course, so all of you are aware about completeness theorem, excuse me, completeness, orthogonality, and Dirac delta function, and all those kind of equations. Okay, so and one more thing, of course, that you need to know about the ensemble average, expectation value, time average. All of these things are are part of the quantum mechanics or the statistical mechanics one. Okay, if you have forgotten, then please revisit to that one once more. And you also need to know about the Born approximation, which is integration to minus infinity to infinity. Any probability is is 1. Okay, and you need to learn how to find out the probability, how to, if you note the wave function, how to calculate the probability density, how to calculate the expectation value. All of these are part of the quantum mechanics one. These will be helpful for your assignment. And if you tell that I let me revisit the formula once, and then today we'll solve two problems within which the all of these kind of problems will come, which will help you to solve the assignment. So first I'll start with the if suppose I'll not go to the very basics, because those comes into the the syllabus of the quantum mechanics one. Our aim is something else, so let me just write the formulas very fast, just to remind you. So the px is the probability density. Then if you calculate the expectation value, then it will be x px dx, which is the expectation value. I hope every one of you can see my if every one of you can see my screen, writing screen. Okay, and now the thing is, if you want to find out the moment, rth order or nth order moment of a random process, then you will find out x to the power r, that is the integration of x to the power r px dx. This is the rth order moment of this random process, of this probabilistic event, whatever you call. And of course, if you find out only the x to the power 1, that is the first moment is corresponding to mean value. Okay, now you need to know one more thing, which is called the central moment, that is x minus x whole to the power r, and the average of that, like in the expectation of that, then x minus x r px dx, which is called rth central moment of x. These formulas are very important. It may come into the examination or or like assignments you have already got, so I think you have checked that this kind of problems are there. Now second central moment is called the variance. The second central moment is called variance, and the square root of this second central moment is called standard deviation. Which is nothing but x minus x square, sorry, this is a variance, which again we can write it as x square. You can calculate it, and it comes like this. In most of the physical situation, this mean and the standard deviation, these are the most relevant quantity in case of probability, right? And in fact, if the random process is Gaussian, then the probability density is itself a Gaussian function, and higher order moments can be expressed in terms of first two central moments. Okay. So again, another important thing, just remember joint probability. Joint probability is, suppose you want to find out the joint probability of x1 and x2, two random variables x1 and x2, then the correlation function among them can be written as this, where p1 x1 x2 is the probability density, joint probability density, and px into dx1 dx2. Okay, so this is what we called is the simplest correlation function definition of simple correlation function of two random variables in x1 and x2. So you see, there is expectation value x just, and just you are finding the expectation value of two random variables with a joint probability function which is p x1 x2, then what you are getting is the correlation function. Okay. So, and sometimes it is this kind of problem can come, as my one of the main motto in this discussion session is to let you know what kind of problem is going to come and how you will solve the problem. So it is important to know that what kind of questions can come and what are the formulas for that. It will be very helpful for you if you write, or I will write up many more things in my writing pad. Maybe you can write write the formulas in 1 or 2 pages, whatever it will happen in 12 weeks, and you will get a formula sheets of all for this course also. That is for your examination purpose only. Other than that, for research purpose, you need to feel the things. I'll try to convey both the feeling and the problems to such that you can perform well in the examination also. Okay. So now sometimes it can happen that joint probability density is given to you. Now they are telling that find out the probability density or probability probability density for the random variable of x1 or x2 or whatever. Then you just need to do p x1 x2 x1 x2 dx2, then what you will get is the probability density corresponding to random variable x1, and similarly px1 x2, if you integrate over dx1, then you will get for the x2. Okay. Again, you can do for the mn and nth order moment of x1 and x2, like x1 to the power m, x2 to the power n, then x1 to the power m, x2 to the power n, p x1 x2 dx1 dx2. This is just the moment. Whatever we do in case of this, the similar thing here with the correlation. Okay. So now we'll change our gear and learn something. That so far we have considered only the real random variables, but in general random variable can be complex. The complex random variables are the most important thing. Okay. The use of complex random variables within a classical theory has many advantages, including the easiness of the calculation. But in case of quantum theory, variables are intrinsically complex, which I have already mentioned while I was mentioning about the wave function. So one cannot do this without these complex random variables. So whatever I am presenting right now in terms of x1t, x2t, now it will become z1t, z1t1, z2t2, whatever, because z is now x plus iy or a plus ib form. suppose z1 and z2 be the two complex random variables and two time correlation function, then it will become just like here whatever we are doing x1 x2, that will become z1 star z2. That means if z1 at t1 and z2 at t2, two complex random variables, then z1 star t1 z2 t2, what we need to find out as a correlation function. Okay, similarly this is to tell you that this is a 2-point correlation, because 2-point correlation because we are correlating between 2 points, whereas you can do it for n, t1 etc etc zn tn. Okay, so it does not matter that how many points you are correlating, but our interest is of course 2-point correlation. That's enough, but that is again complicated. Complex analytic signal representation. Now what we will run, I will not go into the very details of it, rather I need to solve the I would like to solve problems regarding whatever I have told you till now, because then we will not be able to get time. But let us go towards some more thing which I have already taught into the class, that if I talk about this intensity is also a 2-point correlation of field, where VRT is the field and V star RT is the complex conjugate of that field. Okay, now where the field comes from, because anything whatever is there in photon or in light or torchlight light, whatever light is it, we can represent in terms of field, which is V, and this V is a function of position and time. Okay, now these can be written in terms of its Fourier transformation. Always any signal can be written in terms of its Fourier transformation, which is the complex conjugate of the other thing. Here, as I am considering the time as the main variable, as I am considering t1, t2 and the time translation, so VRT, if it is a field, then we can write it in terms of V r omega to the power minus I omega t d omega, where V r omega is the it is the Fourier transform field. Okay, and you can write this VRT always in terms of V star RT plus VRT. That means you can always represent a signal, a complex signal, in terms of its conjugate part plus the real part. Okay, so this is the thing that you need to learn about, and how it comes, that you can try, or either I can show you also. Maybe I can show you that. Suppose if you have something xt, I am considering just x, and this can be anything. Okay, t and omega I am showing any complex conjugate basis, like position, momentum, angular position, angular orbital momentum, polarization h, v, polarization 45 minus 45, anything can be possible. But I am writing now in terms of time and frequency, that if I can write this is the Fourier transform of it, then if I can write also it in terms of minus infinity to 0 x omega to the power minus I omega t d omega plus 0 to infinity x omega e to the power minus I omega t d omega, which can be again write in terms of z star t plus zt. That's why I am telling that any signal can be written in terms of, or maybe you can write it now as x star t xt, but if it is z star z, like the if I am considering it as z, then you can consider it as z also. So z star t plus zt. So basically the thing is that you can represent it as a summation of two part, which is the complex part, which is the minus infinity to 0 part, the complex part, and the plus part, which is 0 to infinity part, for any signal. Okay, so now what is now so I have if I have a field, then it has a v star part and it has a v part, like v star rt and v rt. If I calculate intensity, then this is IRT, which is v star rt v rt, that means at the same time. Whereas if we calculate cross correlation function, which is our main motive to understand, then it is R1 T1 R2 T2, that means V star R1 T1 V R2 T2, which is called the cross correlation function. That means this is the correlation between two same point, the same point, how much they are correlated, same point or same time. And here it is like to different position or to different point or to different time, how they are correlated. And we are mostly interested in this cross correlation function, because when you will interpret with the interference, you will see this is what actually plays the role in the interference. If we do not have these terms, then we will not be able to see interference. Okay, and now I will tell about four essential mathematical concepts which need to know, which are called stationarity, wide stationarity or wide sense stationarity, then the time average, ensemble average, and ergodicity. Okay, these
Madam, hello.
Yes.
Madam, suppose I have electric field.
Yes.
Okay. Let's say E equal to A e की power j omega t. And suppose I want to measure intensity. Okay. So I think that will be complex conjugate of would be A e की power plus j omega t. So I get intensity I equal to A square.
Exactly.
Is it right?
Yes, absolutely correct.
Okay, thank you.
It's absolutely correct, but till now what we have learned is that part only. We have missed one part, which is called the cross correlation function. When I will go in I'll show you that how we will reach to that, and where the cross correlation function is actually hidden up. Okay, so you are absolutely correct that that is the intensity. And in classically or like, I will not mention from classically now on, because even in classically also the cross correlation function is true. Till now we have considered whatever Prashant has told, that intensity directly varies with the amplitude, whatever he has called the A square. Okay, but you will get the intensity without interference pattern when it directly proportional to A square. When there will be a cross correlation function, that means there will be phase, then you will get interference pattern, not a intensity but a fringe pattern or the interference pattern. Okay, so that is the catch, that is the differentiation between a correlation between two same point to correlation between two different point, which arises the interference. Okay, so before going that, whatever I was telling, that we have some important concept which is called stationarity. What is stationarity? Stationarity is like a random process, suppose a random process is there, and random process is said to be stationarity when all the correlation functions are independent of the origin of time. That means whenever we can write a like a t0, t1, t2, and it is the origin time, right? But we don't need to consider this always. Every time if we consider the difference between two other time, then we can do the other calculation or other part. That means we do not need to go back to the origin of the time and consider it again and again. This is necessary for our this is necessary to consider for our calculation as well as for the experiments that are physically feasible. Okay, so for that stationarity, if we consider at its maximum, like stationarity means it should happen in case of first order, second order, third order to nth order correlation. But what we find is that we only calculate up to second order correlation, so we say it is at wide sense stationarity because we are considering only up to second order, like zeroth order, first order and second order. We are considering that up to the correlation function. Whenever we will consider, we can consider the correlation functions are independent of the origin of the time. What does that mean is that the time period, there is a particular time period, that means t2 minus t1 is equal to delta t, t1 minus t0 is also equal to delta t. So that means it's a periodic process, some sort of, but periodic random process. That's why to consider that, we consider that these processes are stationarity in time or position or momentum or OM or angular, whatever you call. Okay, now now the next thing which comes into the thing is that spectral representation of time domain random process, or the mainly the ensemble average also. Okay, so next thing is that I am writing the ensemble average. This thing you already know from your statistical mechanics 1 course. Next thing is that time average, and the next thing is that ergodicity. Now you need to remember these two formulas because these are important for again your assignments. Minus t by 2 to t by 2 PRT dt, whereas this is minus infinity to infinity gamma. Gamma means whenever I will write this big gamma, that means this one, that means correlation function. Okay, this is our way of representation in this course, and as well as what we in generally this scientific community do. So it is better to go with the notation. So the condition of ergodicity is this, or any of these condition, if it is true, then it is ergodicity. Now if you consider, if you ask me about the physically possible experiments, we always consider that process is ergodic process. Okay, and what does it means by the ergodic process? This means that this gamma tau should tend to v0 ensemble average square. It should tend to this rapidly such that a sufficiently long time realization can be broken up into sections of shorter time realization. Okay, that means it is reversible kind of process. Okay, so these were the things that I wanted to mention. Now let us go to some problems, and after doing some problems again, if we get some time, then I will talk about the cross correlation and interference. Otherwise we will discuss about the that part in the next class. Okay, so I hope you can see my this screen where you can see the question. The question, it is telling that the mean x of a random process, like expectation value of x of a random process, is defined as mean x. That is problem I am not writing because I will share this question and slides as well as whatever I am writing in my writing iPad. Everything I will share with you in your everything I will share with you in your in the drive folder link. Maybe I'll once again send you the drive folder link, because that is very important. That is one of the medium to get all of these things. So yes, so you know, I am focusing on this because if you are learning or if you are listening and unable to write something, then no need to worry, because everything will be with you after this class. After the 1 hour you will get everything. Okay, so now the question, it is given as let me write as question 1. The mean x of a random process x is defined as x equal to x px dx, where px is a probability density associated with the random process. I have already told. The standard deviation sigma, which quantifies the degree of randomness of a process, is defined as sigma, which is the second central moment of this x random variable. That also I have defined some time ago. Suppose P1x and P2x are the probability densities corresponding to two separate random processes, which are defined as P1x equal to 1 by A if 0 to A, or else it is 0. P2x equal to 1 by B if A minus B by 2 less than equal to X less than equal to A plus B by 2, or else equal to 0. So what we have is that P1x 1 by A if 0 less than X less than equal to A, or else it is 0. P2x equal to 1 by B if A minus B by 2 less than equal to X less than equal to A plus B by 2, or else it is 0. Assume A greater than B. Verify that the above two probability densities are normalized. Calculate, and question 2 is calculate the mean and the standard deviation of both the random processes. Calculate the mean and the standard deviation of both the random processes. Plot P1x and P2x as a function of x and show the corresponding mean and the standard deviation on the plots. Okay. Of course, even if you don't plot, then also you can calculate. And whatever I am going to do now is to calculate. I think everybody of you can do this problem because this is a very basic BSc first year problem. Preliminary problem. But still, let me start with the basic, because as I wanted to show that this kind of questions are going to come. That's why whatever I am mentioning in the theory part in the first half, that is very important. This is directly from that. So we have first we will verify how. Just 1 by A dx and 0 to A is given, either else it is 0, so it is directly 1. There is no like even, so it is verified first part. And for the second, A minus B by 2 A plus B by 2 integration 1 by B dx, which is equal to 1 by B A plus B by 2 minus A minus B by 2, which is equal to 1. So we have already verified that both the probabilities are normalized. Why this is important? Because whenever you are going to start with any problem, you need to first check that if the probability function is normalized or not. It is, even if it is not normalized, then there is no way to proceed with the further thing, because it should be normalized. It should be normalizable. Now the question B was to calculate the mean second moment and the standard, not the second moment, the standard deviation. And to know the standard deviation, you need to calculate the second moment. So the question is P1x is given as 1 by A, and we want to calculate mean. So mean is equal to x, which is equal to 0 to A x P1x dx, which is 1 by A 0 to A x dx equal to A by 2. Now the second moment, why we need second moment? We need second moment to calculate the standard deviation. So second moment will be x squared, expectation value of x squared, which is 0 to A x squared P1x dx, which is 1 by A 0 to A x squared dx, which is equal to 1 by A cube by 3, that means a square by 3. Now standard deviation is equal to, we have already seen that what is the formula, x squared, that expectation value of x squared and x expectation value of x and whole square of that, so and the square root of the whole of this thing. So now it is a square by 3 minus a square by 4, a 4 minus 3 by 12, a 2 root 3. Okay, and now this is the first part, and second part it is telling about to calculate for the same thing for p2x, and I will not do that. You guys just try it by yourself, because this will be the same thing, same approach. Just do the same calculation, you will get. Okay, so this was the question 1, very simple. Now the question 2. Question 2, it is saying that, first question A, explain what you understand by a stationary random process. What are the conditions for a process to be stationary, at least in the wide sense? Both of the things I have mentioned. What will be the answer? Answer will be, if all the probabilities governing the random process are invariant under the arbitrary translation of the origin of the time, like everything is independent of the origin of the time, then the process is what we call the stationary process. And for a strictly stationary process, all the probabilities need to be invariant of the or the independent of the time, origin of the time. Whereas if at least two things like mean and autocorrelation function are invariant under the arbitrary translation of the origin of time or the independent of the origin of time, then they are called the wide sense stationary. Now question B, it is asking, consider Zt equal to n equal to 1 to n a n e to the power minus I omega n t to be a random process, where omega 1, omega 2, all omega n are fixed frequencies, but the coefficients a1, a2, an are random variables. What are the conditions that ensures that Zt is at least a wide sense stationarity process? For that, what do you need to do? First condition is that your mean of your random variable should be 0, and second is the autocorrelation function, which should be just dependent upon if both of the things are if that is that is independent of origin of it. That means at that point, whenever the two variables will be same, then only it will be a value, otherwise it will be 0. Okay, so what does it it is just this question just depicts that what do you understand mathematically about wide sense stationarity. And I will again say that if Zt is a wide sense stationary process, then mean should be independent of time, and autocorrelation function should depend only on the time difference that I have already mentioned here, that this should be only delta t, the difference between these, not the time t1 t2, rather t2 minus t1. Now you have to represent it in terms of mathematics. First I will write the mean, and second I will write the autocorrelation function for this field. Okay, now what will be the condition that you will find out, because this question is already there in your assignment, and I hope I have given enough hint. Again I will give hint that what will be the condition, how to understand that. So the question is Zt equal to n equal to 1 to capital N a n e to the power minus I omega n t. This is a random process. And what are the random variables? a1, a2, an. These are the random variables. Now what will be the mean for this function? That will be nothing but this. What will be the autocorrelation? Tau I am writing as delta t is the tau, that is the time difference. That is equal to z star t, z t plus tau. Then we can write it as n equal to 1 to n, and these are some dummy variables. We can write it as n m, m equal to 1 to n, a n star a m e to the power I omega n minus omega m t e to the power minus I omega m tau. Okay. Because now it will become omega n corresponding to n, and it will become omega m corresponding to m, and there will be a function which is I omega m tau, because it just only depends upon the difference of the time, not the origin of the time, neither the two different time. It only depends upon the difference of the two of the time. So now we can write it, the mean can be written as like this, and autocorrelation function can be written as this. Now for Whiteson stationarity, mean should be independent of time, and autocorrelation function will depend on time difference. According to these two conditions, find out what will be the condition in terms of mathematics. I will not tell, as it is already there in the assignment, but I have given you enough hint. So this was the question B. A I have already mentioned verbally. Now C is explain stationarity and ergodicity. Does stationarity does one imply the other and vice versa? So for this, I will again say what is stationarity and what is ergodicity, that I have mentioned, but let me say once again. A random process is said to be stationary if the probability distribution for the random variable is independent of origin of time. This implies that all the moments of the distribution are also invariant under the time translation. A random process whose various ensemble system realization also shows the behavior of a single system over a long period of time is called ergodic. Or in terms of other words, what I told earlier is that if we realize the system for a sufficiently long time, then it can be broken into sections of shorter time realization, each of which still remains longer than the time period of it, that means the tau. Okay, so this is the condition, this is the definition of the ergodic process. So for an ergodic process, the time average of a quantity for a single system over a long time is equal to the ensemble average of the quantity over many system realization. That means ergodicity necessarily implies stationarity, but stationarity does not mean ergodicity. Okay, so let me write it in terms of just this word. Ergodicity necessarily implies stationarity. but I can write but converse is not true. Okay, again remember, ergodicity means we can realize the same system over a long period time into a shorter period of time. That means the system realization also reflect the behavior of a single system over a long period of time. Or you can other way say that long time realization can be broken up into sections of short time realization, and each of that short time realization again are enough longer than the time period of tau. So this is what is the definition of ergodicity. And stationarity I have already mentioned several times. So at the end what we understand is that ergodicity necessarily implies stationarity, but converse is not true. Now if the mean of a random process is 0, question D, then what it is given as z omega equal to 0. And if the different frequencies are completely uncorrelated, that is z star omega, z omega and some average of that, then s omega equal to delta omega omega dash, that means totally uncorrelated, then prove that the process is stationary at least in the wide sense. Again, let me solve this problem. Jt, what it is written? What it can be written as like this: z omega to the power minus I omega t. I have already mentioned this, that everything can be written in terms of its Fourier transformation. This means z omega e to the power minus I omega t d omega. Now it is told that it is given to you that z omega is equal to 0. Utilize that, it becomes 0. Okay, so they asked they asked you to show that the process is stationary. That means you need to show the mean is not depend on time or 0 and the correlation function also does not depend on the origin of the time, rather it depends on the difference of the time. So now I will calculate z star t1, z t2, which is of course now 2 integration z star omega z omega e to the power I omega t1 e to the power minus I omega t2. Maybe one is omega, one other is omega dash. These are dummy variables. D omega dash. Then what we'll get is z star omega z omega dash e to the power minus I omega I omega dash t omega t1 omega dash t2. But if omega is equal to omega dash, that means it is as it is already mentioned that z star omega z omega is equal to s omega delta omega minus omega dash. I will substitute that to here. Then what we will get is s omega. Let me write the previous step. S omega delta omega minus omega dash e to the power minus I omega t1 minus I omega dash t2 d omega dash. Please revisit the Dirac delta function equations and integrations once, such that you are able to get the Dirac delta integration, because there will be lots of Dirac delta integration in this course. Then what you will get is integration s omega to the power minus I omega t2 minus t1 d omega. That means now it becomes s omega to the power minus I omega tau d omega. That means it only depends upon the difference in the time, and it is 0. That means this is a wide sense stationary process. And last part, which is E, is telling us that consider a function v phi. V phi is equal to 1 for phi 0 minus phi 0 by 2 to phi 0 by 2, whereas 0 otherwise. If v phi has a decomposition of the form v phi equal to L equal to minus infinity to infinity alpha L e to the power minus IL phi, that means calculate the weightage alpha L square of the decomposition. Okay. So what do you need to do? First, okay, let me do, like I have this equation, right? Let me take the integration in both sides. V phi e to the power IL dash phi d phi. Integration minus pi to pi, L equal to minus infinity to infinity alpha L e to the power minus L phi e to the power IL dash phi d phi. Okay. Now minus pi to pi v phi e to the power IL dash phi d phi will become L equal to minus infinity to infinity alpha L minus pi to pi the power minus I L minus L dash pi d pi. That means the right hand side, this part has become now the Dirac delta again. You should have one motivation in every integration problem here, that there will come two kind of integration. Either it is Dirac delta or it is a special kind of integration, gamma function integration, which I will show later, that kind of problem. Two types of problems, two types of integration always you will get. One is Dirac delta, another is a special gamma function problem, gamma function integration. Okay, so it's about IL dash phi d phi. Now I can write it as L equal to minus infinity to infinity alpha L 2 pi delta L L dash. So now I can write it as v phi e to the power IL dash phi d phi equal to 2 pi and alpha L L dash. So again L dash are dummy variables, so L dash and integration pi to pi, and then L dash or L does not matter, that's what mean by dummy variables. I am just considering L dash just for represent two different things, and it can again and again change between themselves, that's why they are dummy variables. Okay, so if I write alpha L, then it will become 1 by 2 pi integration minus pi to pi v phi e to the power IL phi d phi. Okay, now substituting the conditions which are given over there here. Okay, so alpha L now 1 by 2 pi minus pi 0 by 2 to pi 0 by 2, it will be e to the power IL pi d phi. So alpha L equal to pi 0 by 2 pi sinc function. How it comes sinc function, that you can check once. Okay, so this will be the function, and now you are very well to know that how to, I mean, even not give this just solve this integration, that will be the answer of your question. As well as if you find out the square of that thing, alpha L square, then what is it is actually asking, that calculate the weightage alpha L square of the decomposition. So finally you need to calculate alpha L square. So just do this integration and you will see what is actually coming, that is the answer, that the square of that is the actual answer. Okay, so this is all that I want to do for today's mathematics and problem solvings, because if you can grasp all these things, all these calculations, then I think it is just what you need to do is that go through the questions again and again, try to solve it by yourself. I have already shown you some glimpse that how to solve the questions, but you need to understand it by your own, that why I am doing this. And these are all very basic problems, let me tell you, because eventually you will get more and more difficult problems. But today it was enough. I have introduced with a lot of different concepts today, as well as I have motivated you enough to learn about coherence and then entanglement, and why we are talking about coherence and correlation. So that was a part of today's discussion session. This is all. More than that, if I tell anything more than this today, then that will be excess, I think. So maybe today I can stop here, and today I can stop here. But before that, again, I will ask you that whatever it is happening, just go through them one by one. Make a very systematic note or systematic points that what are there. These are very the problems whatever you are going to get in the examination or assignments, though those will be very much systematic approach, not like very random things. So if you track I mean, obviously it will be some sort of conceptual, but if you get that, if you keep the track of the formulas, then at least you will not feel any difficulty to understand which formula and which condition we need to know, because several things will come. And integration, I have already mentioned, you need to revisit the Dirac delta as well as gamma function. This kind of integration, two integration we will use here a lot. And then apart from that, Fourier transformation is one of the very important thing here, and quantum mechanics 1, statistical mechanics 1. These are all the things that you need to go and check it out, and such that you can you can speed up the process, and you will enjoy. This is the first day, and a lot of things I needed to tell, and I hope everybody has already seen the lecture. So you may or may not feel the difficulties. I don't know what is happening with what is the condition, but I will try my best to convey these things to you. If you find anything, any problem regarding this, you just you have you have three options. If you are coming here in the direct in this discussion session, live discussion session, then it is very helpful. You can always ask a question to me directly here. And if you have if you are not able to attend the class somehow, or miss some part of this, then you can always go to the YouTube link. I will share the YouTube link once again, and it will be uploaded, the session will be uploaded after within 1 hour of this. And then you can again ask question in the chat box of YouTube. You can always mail me regarding any kind of problem regarding this course. I am writing my mail ID. This is my mail ID. And you can also write a question in the ask a question portal, where any of us whoever are there in this our team, we can answer you that regarding this question, regarding your question. So these are the three platforms through which you can keep in contact with us. Please ask question, enjoy the process, and I'll try to learn as much as possible for you. So this is all for today from my side. Maybe I will just show you once that what we have done today is that we have solved few problems. We have learned the essential mathematical concepts of stationarity, ensemble average, time average, and chronicity. We have learned about the complex analytic representation of a signal. We have learned what is the coherence and correlation, what is second order correlation. We have revisited the joint probability. We have revisited the mean, standard deviation, rth order moment, rth order central moment, etc. And also we have discussed, most importantly, the difference between classical and quantum mechanics, and what is interference, and where the coherence comes into the play, and what do you mean by the coherence, and why correlation function is so important. So this is why I wanted to convey in today's class. I hope everybody has enjoyed, and if you have any comment, please let me know. Okay, so if you have any comment now, you can tell me. If you have any question now, you can tell me. If you don't have at this moment, but later, you can contact by these three platforms: ask a question, YouTube, or mail me directly. I think this is all for today's class, and I hope that everybody will come and attend the next next sessions also. So hope you guys have enjoyed, and see you soon. Bye.